Put your pencils down and pick up your colored pen. We'll see how we did with the last lesson, which was part 1 of this lesson. You can see today is titled Lesson 3-4 Part 2. We're going to continue where we left off and build on what we know. So let's see what we know. Here is the table that I used to produce the graph. Yours should look very similar. The goal, of course, is to get this column of ordered pairs. And using those ordered pairs, we graph. This function is discrete because we were given a specific domain to use. So we cannot draw a line through here because we do not know if anything exists between these 2 points or between these 2 points or here or here. So we cannot draw a line through them because it's discrete. The first thing I would like to talk about is how we get from here to here. We have a whole bunch of people who know already. Oh, okay. So hold on. Let me catch up to you. Let me rewrite the original. The original function is 1/2 x equals y minus 3. How do I get from here to here? What was the first step? We'll start with Sean and then Natalie, and then we'll go to Von Travius. Add 3 to both sides. Natalie, is that the same thing you did? Okay, so that makes this disappear. Remember, we put the x term first. We get 1/2 x plus 3 equals y. But that's not what it says. It says y equals 1/2 x plus 3. So how do I get from here to there? Natalie, what'd you do now? Okay. So if everyone will pause for a moment and look over at my wall of properties, and I apologize if you're sitting like right on top of it, find the sign that says wall of properties, and then look immediately to the left, and there's a property called the symmetric property of equality. And you're going to start using this today, and you're going to use it for the rest of the year frequently, and you're going to use it a ton next year in Geometry Honors. The symmetric property of equality says that if you have an equation where the 2 sides are equal, you can flip it around. So all we have to do is flip the whole thing around, and we get y equals 1/2 x plus 3. We want the y on the left because we want the variable that we're looking for. This is what we're looking for. The value of y, we want what we're looking for to be on the left. That's the whole point. Does anyone have any questions about how to translate the equation? Are there any questions on anything else? Give me a thumbs up if you got it right. Okay, put your thumbs down. Emily, where'd you go wrong?
I accidentally added 3 to the half instead of adding it to the equation.
So you combined these when you were not allowed to. Okay, and that messed up the whole thing. Do you see why now that you cannot do that?
Yeah.
Very good. Thank you for sharing. Daniela, where'd you go wrong? You did the same thing. Okay. Kiana, did you make the same mistake? Okay. So there's a case where our team kind of crumbled together, but that's okay. Tatiana, where'd you go wrong? Oh, you did the same thing as well? Okay. So that's the idea of combined like terms. You have to know what you're allowed to add together and what you're not allowed to add together, and those may not be added. Don't worry. By the end of this year, it will be second nature. It will be like no big deal. Any other comments or questions? Good. Let's draw a line across our papers and jump right into part 2. And first, I would like to offer a summary of what we know so far. And I've got this graphic organizer. I have a computer to help me make this. I don't need you to draw these funky arrows. Just draw a simple arrow, it's no big deal. But the idea is to know all these different terms that mean the same thing. Independent variable. The domain is the collection of values that represent the independent variable. Then we've got x value means independent variable, x means independent variable, and input means the independent variable. So these all mean the same thing. Likewise, dependent variable has all these terms associated with it. The range is the collection of values for the dependent variable. The y value. Function notation, f of x is the same thing as the dependent variable, and then output. So we're using these ideas to draw pictures, because the pictures tell us things that the data itself wouldn't tell us. That's the whole point of what we're doing. Creating a picture to help us interpret a situation. Now, you don't even know it yet, but you remember how independent and dependent I referred to your science teachings from last year? Well, you don't realize it, but you're actually in the process of learning part of a scientific research process. And when we get to the end of this unit and some of the other things we studied, you're going to be equipped with tools to actually do real research and to actually draw conclusions from doing surveys and research and exploring by asking people questions. So that's really our goal. So, I do not need you to copy this. I need you to read this. And then we need some basic ideas that come out of it. So, this is the difference between today and the last lesson. Today, we're going to explore what happens when we're not given a domain, but the domain is all real numbers. When you are told that you are to use all real numbers, or as it says here, if a domain is not given, you assume that the domain is all real numbers, that means any number can be used. In today's warm-up, only -2, 0, 2, and 4 were allowed to be used. That was a specific domain, and that's what made this discrete. But now we're going to explore scenarios in which all real numbers are used. That means any number can be used as the input value. And that means we get infinite ordered pairs. Well, if I asked you to write all the ordered pairs for a function and I said they're infinite, keep writing until you get all of them, you'd never finish because it's infinite. It goes on and on forever. So that doesn't make sense. So to be practical, instead, what we do is we pick a few of the ordered pairs, graph those, and then we draw a line through them. The line represents all of the other ordered pairs that we didn't write down. And then we draw arrows on either end to indicate that it goes on and on forever in both directions. So this is our goal today, to explore these situations. Are there any questions so far? Good, let's jump right in. Graph the function -4x equals y minus 2. The process is the same, but there's a couple of things that are different. So I'm going to relate this question to the warm-up. So I'd like you to put your pencil down for a second, and I'll tell you when to pick it back up. And I want you to just watch. The warm-up question was actually similar, but there was something written right here. So let's go back and take a look. That was there. Well, now it's not. Because now we're being asked to do this. So now there's nothing here, which means that we automatically assume that we are going to use all real numbers. So if there's a domain there, you must use the domain. If there's no domain written, then you use all real numbers. So how does that impact the process? Well, and I asked you to put your pencil down for a reason, leave it down for a second. Here's the process that we learned last time. Step 1 was to rewrite this so that it was y equals. So that's still going to be step 1. And so we still want to figure out y equals. Step 2, we made a table of values. And we're going to take the training wheels off, so we're just going to use the 3 columns. Because you should have enough experience now to know that an ordered pair comes from the x and the y. So what happened last time when we were given a domain is this went right here. That's still going to happen. But Jacob, the part that's different is that before, this domain went right here. That's still true. However, we don't have a domain given to us. Does anyone know what we do now? How do we get the numbers that are going to go right there? Where do they come from? Von Travis, what were you thinking? Say it again. Random numbers? Like, what do you mean? Where do those come from? Where'd you just come from? Where'd you just get 2, 4, 6? You just guessed, but where did it come from? Yeah, it comes from your brain. So instead of the numbers being given to us, they come from your brain now. Usually, there's a simple set of numbers to use. Sometimes it won't work. So we're going to talk about that in a moment. Okay? So now you can pick up your pencil. And now let's go back and start the process. Step 1. So now we're right here. Here's the original function. We want it to be y equals something. So what's the first step to get us going? 1, 2, 3, 4, 5, 6. We'll start with Ethan, Shannon, and then Melinda. Ethan. Beautifully said. Add 2 to both sides will get us closer to y equals. But remember that these are not like terms. So you can't add them together, and we put the x term first. So it's going to be negative 4x plus 2 equals y. But how do we get now from here to y equals? Shannon, you were next. How do we get there? That thing? Yeah, what is that thing? Good. Nothing to be worried about. You said that perfectly. The symmetric property of equality says we can flip it around. So now we have negative 4x plus 2. So we accomplished our goal. We got it into the form y equals. So now that goes right up here. Y equals negative 4x plus 2. Now I have to give you a moment to construct the table. separate. So I'm just pausing to give you a moment to catch up with step 2. Now, to construct a legitimate graph, we want a minimum of 4 points. A minimum of 4. So that means we need a minimum of 4 input values. As von Travius helped us understand, they come from our brain. But usually you can keep it simple. Numbers like 1 and 2. But 0 is really easy. So you want to use 0 frequently. And then you also want to make sure you always include at least one negative number. Because we want to see what happens on this side of the graph. We don't just want to see what happens over here. We want to see what happens on this side. So we need to use at least one negative number. So here's the set of numbers we're going to use often. -1, 0, 1, 2. Sometimes that won't work, but frequently it will. Now let me pause for a moment and say that since the domain is all real numbers, if I wanted to, I could be wacky and crazy and I could put 1/3 and I could put -0.98 and I could put -200 and I could put +1000. Those are from the set of all real numbers. But that means that one of my ordered pairs would be 1000 comma something, and that I would have to build a graph that could fit that. And then I would have 1/3 comma something, which means when I go to my grid, I would have to estimate 1/3 of the way across. That's not practical. So since that's not practical, we don't do that. We do what's practical. So that's why we use -1, 0, 1, and 2. And now those are our inputs. Plug them in, get the outputs. So now we've got -4 times -1 plus 2. Simplify and put the output. -4 times 0 plus 2. -4 times 1 plus 2. -4 times 2 plus 2. Go ahead and take 30 seconds to simplify that and get your output values. Make sure you're careful with computation. Don't do incredibly difficult algebra and then mess up with computation. That's tragic. Bless you. So, completed table. And the whole point was to get this and this. And remember, the training wheels was we added a column to write the ordered pair, but you should now be able to tell that's -1 comma 6. And that's 0 comma 2. So now we're going to go ahead and plot the points. So take your ruler. And yes, we use rulers and we use the grid of the graph paper to be precise and accurate. So take your ruler and set up a grid and start plotting the points. We've got -1 comma 6. Zero, comma 2. 1, -2. 2, -6. So you should now have a graph that looks like mine, but we're not done because today's graphs are different than last time's. So let me review one of the differences. The domain is all real numbers, which means we were allowed to pick any number. Remember those wacky numbers that I put up? Those were all allowed to be used. They just weren't practical. But they are part of the domain. Which means that this is not a discrete graph, it's continuous because there does exist information in between. But would it make sense to do this? Remember I was talking to you about infinite ordered pairs? Would it make sense for us to have to do this? Put a dot for every ordered pair and keep going and going and going and going until we finish? That wouldn't be very much fun, and that would not be very efficient, nor would it be practical. And so what we do instead is we draw a line to represent all those points. But you need your ruler, and your line needs to go through the points, not connect them, but go through them. So here's what it needs to look like. It's going to go, it's going to go through the last point. We put an arrow on the end, and it's going to go through the last point down here as well. And we put an arrow on the end of that side. The arrow indicates that it goes on and on forever in both directions because it's infinite. Does anyone have any comments or questions on why it's continuous, how to make it continuous, anything at all? Any comments or questions on how we got step 1 done, or step 2, or how we went from step 1, step 2 to step 3? Any questions at all? Okay, so this was 1A. Let's go to 1B and look at a slightly different scenario, but same idea. We want a picture. Graph the function g of x equals the absolute value of x plus 2. Now, writing step 1 and writing step 2, like writing those words, that's a training wheels technique. We don't have to do that anymore. We know what we have to do for step 1. So it doesn't matter whether you write step 1, but you need to do step 1. So I don't care if you write it, and I'm not going to write it anymore. I don't need the training wheels. So I'm just going to do step 1. It's not something you can skip over. Step 1 says we need the function written so that it says y equals something. Well, there's no y there at all. But you should remember that what I am asking you to do is anytime you see function notation, g of x or f of x, you immediately put a y in its place. And so in essence, y equals absolute value of x plus 2, that is our function. Step 1 says to get the y by itself. Well, the y is already by itself. So step 1's done. Step 2 says to make a table of values using that function. So we're ready for step 2. I don't need to write step 2. I just need to do it. That's going to be x. That's y equals absolute value of x plus 2. And that's your y. But this does not give us a domain. It doesn't say for domain and specific numbers. So the domain comes from our brain. What would be a good domain to use this time? Any suggestions? Sure. -2, 0, 2, or 4. I would just use -1, 0, 1, and 2 again. but I want Deja and a few other people to do -2, 0, 2, and 4 so that we can see what happens. Because it doesn't matter. You should get the same picture no matter what. So now take the inputs, plug it in, and get the output. Absolute value of -1 plus 2, absolute value of 0 plus 2, absolute value of 1 plus 2, and absolute value of 2 plus 2. Should be mental math for you at this point. Does anyone have any questions or concerns about how we got this done? So we're going to graph in a moment, but before we do, let's see who's operating at a really high level today. Let's see who remembers. What shape does an absolute value equation usually form? We've seen it a bunch of times already. Nobody remember? That's okay. You'll remember after today. So let's see what shape it forms. So now we're going to plot the ordered pairs. -1, 0. I'm sorry, -1, 3, 0, 2, 1, 3, 2, 4. So plot those points on a grid. But the whole point today was that we are dealing with functions whose domain is all real numbers, which means that this is going to be a continuous graph. So now we have to add in the continuous part. But you have to be careful with absolute value ones. So does anyone recognize the shape now, even though it's a little hard to see? What's the shape going to be? Let's add in one more point. We'll do it mentally. Let's do -2. Plug in a -2. -2 right there. What would the output be? I'm sorry, not a negative. Yeah, -2. Sorry. -2. What would the output be? Aaron? So -2, 4 is also one of the points. -2, 4, right there. So what shape does it form? Tatiana? Sort of. All right, so let's complete the graph. This time, it doesn't go like this because these actually don't exist. What happens is it actually goes to here and then bounces back up. So this is what the graph looks like for an absolute value. It actually goes this way on and on forever. And then it starts here again and goes this way on and on forever. And it forms a V. For those of you who haven't caught on yet, the line represents every solution to the function.
We're going to do the presentation teacher we're on the luncheon in here, but I don't have a phone from my computer to hook it up. If I send it to you, the presentation's on Keynote, can you bring it over there when
Okay, so the line represents all the solutions, which means that if I pick this point right here, that's on the line, correct? If I find the coordinates of it, -3, 1, 2, 3, 4, 5, -3, comma 5. If I plug -3, comma 5 into this, it should be true. -3, absolute value of that is 3, 3 plus 2 is 5. It works. No matter what point I pick, anywhere on here, and going on and on forever, it will always make the statement true. Does anyone have any questions about that? Any questions on how to construct a graph? Okay, let's see how you do on your own. Checkpoint number 1. Graph the function y plus 2 equals 3x. The last group got 5 minutes, you get 4. Which means you got to work. 1 minute to finish and to team talk. Compare your graphs with your teammates. You're going to have to actually move your papers so that you have them side by side.
It's right. I know, but still, because they almost had numbers. Yours looks like it's going like that. Ours looks like it's going like that. Ours is more steep than yours. Oh. See, yeah, it's not the same. Look. See, no, it's not the same. It has to go steeper. Yeah, she did it. Look. Right here, see, look. Yours goes like that. Hers goes like that. How are you going to tell?
All right. So, now compare yours to what I have. Here is the graph. And so these were the points that I got from this table. And so I use the same set of values. Again, you don't have to, but we use the same set of values because it's practical. So these are the ordered pairs, and then the line goes through it. The computer program I use to make the graphs doesn't let me put arrows, so I have to draw those in. Any comments or questions on how this was done? Give me a thumbs up if you got it right. Good, put your thumbs down. So we're going to go right into checkpoint number 2 and see how you do with this more challenging, higher level function. So, you got 4 minutes again. Any questions or concerns, please let me know and I will come to you to assist. Or ask a teammate quietly. about a minute left. Okay, no team talk this time. This time, just compare yours with mine. Here's the graph. And there should be arrows on the I actually used 5 points on mine, but you should have had 4 or 5, doesn't matter. Either way, it forms the same graph. Anyone have any comments or questions about checkpoint number 2? Aaron and then Von Travis? I'm sorry? What do you mean solving? Okay? So the 3-column table I'll sketch quickly. We've got x, we've got y equals absolute value of x minus 1, and we've got y. I already know where most of my students messed up. The set of values that most of us used was the same set that I had suggested. But then you put it in here, and then you did not know what negative 1 minus 1 was. What's negative 1 minus 1? Angela? Negative 2. And the absolute value, because now you have to take the absolute value of that negative 2, that's positive 2. Then we've got y equals absolute value of 0 minus 1, which is negative 1, but the absolute value of that is 1. Y equals the absolute value of 1 minus 1, which is 0. The absolute value of 0 is 0. Here's the big difference. 1 second, Von Travis. Y equals the absolute value of 2 minus 1. That's also 1. So notice that we've got 2 outputs of 1. And that's why we have 2 points that have the y value 1. Von Travius, what was your question?
For the first one, I put negative 2, and then I came up with 3. And my graph didn't look like that because kind of like a trapezoid.
Okay, well, negative 2 comma 3 is right here.
Oh.
So I actually used in my original graph, when I constructed this using the computer program, I used negative 2 comma 3 also. So that was another point. We could have used 3 comma 2, 4 comma 3. Any of these points are on the line, negative 3 comma 4. Any of these points are on the graph. Okay? Any comments, questions? Aaron, is it making sense now? Okay. So now, we need to be able to apply this in the real world. And I don't want you to copy this at all. I want you to read. And that's supposed to be in real world situations. Take a moment to read. Should take you about 30 seconds. I indicated earlier that the whole point of everything we're studying is to be able to actually go out into the world and do research and draw conclusions from your research. So the real world has some limitations that a math classroom doesn't have. For example, time is never negative. There's no such thing as negative time. Distance is never negative. The number of people is never negative. So in these situations, you actually have to think carefully about your x values that you're choosing, because you can't put a negative number of seconds or a negative number of students. It doesn't make any sense. So in the real world, you have to pay attention. In these situations, we use non-negative values. Non-negative means positive and 0. When we have just those values, that means that the graph will be totally in quadrant 1. And so when we do the graph, we will only need quadrant 1. So we're going to explore a real-world scenario. It's a very simple scenario, but we want to get this idea. So, example 2. You do not need to copy the question. You just need to write example 2 and then read the question. And we've got some research based on some wacky scientist. So there's a wacky scientist out there somewhere who was fascinated by the fact that a mouse, which is like this big, with tiny, tiny, tiny little legs, could actually move really fast. 3.5 meters per second is really fast. A meter is like this. So that means a little tiny mouse can move 3.5 of those in a second. That's really fast. So he was fascinated by this, so he did some research, and he found that on average, a mouse can run approximately 3.5 meters per second. So he actually took mice and documented how fast it moved from one point to another and figured out that on average, that's what they ran. So let's look at how he figured this out. He had a graph and he came to the conclusion. So let's take a look at what happened. So here's the function that he came up with, y equals 3.5x. And we want a graph of this to see how the movement of a mouse looks. So it's the same process. It's the same process that we've gone through. We need the function written as y equals. Well, it already is. Then we need a table of values. And we're going to take the training, we're going to keep the training wheels off. We only need 3 columns because we're becoming expert level at this. We just need x comma y. And y equals 3.5x. But here's where we have to be thoughtful. This is a real scenario. And we're talking about a mouse running x seconds and covering a distance in meters. So we have to choose x values to test out. We cannot choose a negative number because it wouldn't make sense. So what do you think we should use as our input values? What would make sense? Only one person can try to figure it out? Okay. Oh, we have a bunch of people. Okay. Mark and Melinda, what do you think?
2, 2.5, 3, 3.5.
Okay. What were you thinking?
1, 2, 3, 4.
Okay. Aaron, what were you thinking? Okay. So I would say you're going to do yours, and you're going to do yours, and you're going to do yours. I would say the simplest thing to do would be 0, 1, 2, 3, or 1, 2, 3, 4. Usually you want to throw in a 0 there to see what happens right around there, but you could get away with not doing it. But we're going to do 0, 1, 2, and 3. And so we just follow the process that we've been taught. The only difference is we don't have any negative numbers. So 0, plug it in, we get 3.5 times 0. Well, that's 0, which makes perfect sense because if the mouse is traveling for 0 seconds, it's not going anywhere. And then we have 3.5 times 1, and 3.5 times 2, and 3.5 times 3. And so its distance will be 3.5 meters, and then 7 meters, and then 10.5 meters. Does anyone have any questions on how we constructed the table? This is the difference between real world and math classroom examples. Real world can be negative in many cases. Any questions? So now a graph of a real world scenario. The graph, since everything is positive, there's no negative numbers here and there's no negative numbers here, we only need quadrant 1. But we need to label our axes because this is a real world scenario. So the independent variable was time in seconds. So down here is going to be time in seconds. What's the dependent variable in this case?
Distance.
Is distance, measured in meters. So this is going to be distance measured in meters. I have lots of room on my graph, so I'm going to go by halves. You can decide what you want to do. So I'm going to do 0, and then half a second, and then 1 second, and then 1.5, and then 2, 2.5, 3, 3.5, 4, and so on. And then I'm going to go by halves going up as well. That's 0. That will be 1. I just barely fit it in. And so now we can plot our points. 0, 0 shows up right there. Pick it. And then 1, 3.5, 1, 3.5 will be right there. And then 2, 7. And then 3, 10.5, right all the way at the top there. And because the mouse is running this entire time, this is continuous because even though we put a point at 1, 3.5, he was running in between 0 and 1 because that represents time. So this is a continuous graph. That means we draw a line connecting, but it's real world. So we will have an arrow on this end, but no arrow on the other because it cannot go below 0. And so now we have a real world scenario. Does anyone have any questions on how we put the graph together? We were also asked another question. Use the graph to estimate how many meters the mouse can run in 2.5 seconds. So this is one of the benefits of a graph, is that you can look and immediately know the answer. So if I just look at 2.5 seconds and travel up the graph, I will hit somewhere around right there. Which that's 8, that's 8.5, and it looks like it's halfway between 8.5 and 9. So I would say that would be about 8 3/4 seconds. I'm sorry, 8 3/4 meters. That point is 2.5, approximately 8.75. That's seconds, that's meters. So the answer to this question up here is, how far would it travel in 2.5 seconds? It would travel about 8.75 meters. That right there. Any questions on how we did that? Any concerns? So the point of the real world was the constraints, that you could not use negative numbers. Are there any concerns at all? So we were going to do a checkpoint, but unfortunately I've ran out of time. That's my fault, not yours. So we're going to go straight to our homework. So draw a line across your paper. Your homework is Lesson 3-4 Part 2 homework worksheet, which I'm going to hand you in a moment. And you're doing numbers 27 to 36 and 40 to 43. And the next assessment you're going to have is your quarterly, which is next Thursday, I believe. Let me double check.
Yes.
Yeah, it's Thursday.